We're ready for the next set of examples. We've got a whole bunch of rules to apply now that we are going to use as we go in our examples. And our first example, we have the integral of 3x cubed dx. First thing I'm going to do is I'm going to apply the constant multiple rule for integrals, and I'm going to pull the 3 out front. So we get 3 times the integral of x cubed dx. And then we can apply the power rule for antiderivatives to our x to the third. And that power rule for antiderivatives says that we are going to add 1 to the power, so we'll get x to the fourth, and then we divide by the new power, plus c. So we can rewrite this as we want, if we want, as 3x to the fourth over 4 plus c, or we can rewrite it as 3/4 x to the fourth plus c. Those are all the same. All right, that's example 1. Example 2, we have the integral of x to the 8th dx. And here we don't need to pull anything out of the integral. We can just simply use the power rule for antiderivatives. So we're going to add 1 to the power and divide by the new power. So we're going to get x to the 9th over 9 plus c, which we can also rewrite as 1/9 x to the 9th plus c. Now we're ready for the next example. All right, example 3. Here we have the integral of 10x squared minus 2 dx. For this I'm going to apply first the sum and difference rule that will allow me to break this up into 2 integrals. The integral of 10x squared dx minus the integral of 2 dx. And then I'm going to apply the constant multiple rule in both cases. So we're going to get 10 times the integral of x squared dx minus 2 times the integral of 1 dx, because that's 2 times 1. We don't strictly have to do this step. We could just leave it as 2 dx and then find the antiderivative from there, but I want to show you how all of the rules apply here. Now we have 10 integral of x squared dx, so that's going to be 10 from our constant multiple, which we're going to multiply. We're going to apply the power rule now to the x squared, and that's going to give us x to the third over 3. And then we have minus 2, and then we need to find the antiderivative of 1. Well, the antiderivative of 1 is just x. So now we get plus c. So this will give us 10x cubed over 3 minus 2x plus c. Or we can write that as 10/3 x cubed minus 2x plus c. And that brings us to the end of example 3. And on to example 4. All right, example 4, we have integral of dx. And it looks like we're being asked to find the antiderivative of just nothing, but that's not actually the case. We just want to realize that the dx is the same as 1 times dx. So we're looking for the antiderivative of 1, and that is going to give us x plus c, because if we take the derivative of x, we get 1. All right. Next example, we have the integral of 1 over 3x squared dx. Now, first thing I'm going to do here is I'm going to use the constant multiple rule. But to use the constant multiple rule, I'm first going to rewrite the 1 over 3x squared as 1/3 times 1 over x squared dx. Now I can use the constant multiple rule and pull the 1/3 out in front of the integral. So we get 1/3 integral of 1 over x squared dx. And now, just like with derivatives, sometimes it is easier for us to work when our expressions in this form, where we've got these rational expressions, are actually written in the exponential form, where we're just looking at the powers. So I'm going to rewrite as 1/3 times the integral of x to the negative 2 dx. And now we have the integrand, the x to the negative 2, in a really good form for using the power rule for antiderivatives. So we're going to get 1/3, that's from the constant multiple rule. And then we're going to have x to the negative 2 plus 1 over negative 2 plus 1. Negative 2 plus 1 will give us negative 1. So this is 1/3 times x to the negative 1 over negative 1 plus c. And so this will be, I'm going to pull the negative out to the front, negative 1/3 x to the negative 1 plus c. Or we can rewrite the x to the negative 1 as 1 over x. So we're going to get negative 1/3 times 1 over x plus c. So it's really important to remember that when you have fractions in that form, that for applying the power rule for antiderivatives, it is much simpler for us, much easier if we convert that into the fractional form. Sorry, not the fractional form, the exponential form. We've talked about this before, that sometimes the fractional or exponential form is better. The fractional form is usually nicer if we're looking at it and understanding it and trying to solve with it. But if we're trying to apply a power rule either for derivatives or antiderivatives, it's better to have it in the exponential form. Okay, so we are ready for number 6. All right, number 6. We have the integral of 3 over x squared dx. And this looks very similar to the problem we just did, but it's not quite the same. I'm going to start out again by using the constant multiple rule to pull the constant out front, but before I do that, I'm going to rewrite 3 over x squared as 3 times 1 over x squared. And then we can pull the 3 out using the constant multiple rule for integrals, and we'll get 3 times the integral of 1 over x squared dx. Now, just like in example 5, we want to rewrite the 1 over x squared as x to the negative 2 so that we can easily apply the power rule. And then we'll have 3 times x to the negative 2 plus 1 over negative 2 plus 1 plus c. So that's going to give us 3x to the negative 1 over negative 1 plus c, which we can rewrite by pulling the negative out front. So it would be negative 3x to the negative 1 plus c. Or if we wanted to rewrite in the fractional form, this would be negative 3 times 1 over x plus c. Or if we go even farther, negative 3 over x plus c. And as we've talked about before, there are various reasons to want it in one format versus another. All right, so you should be ready to turn the page. So while you're getting ready to turn the page, I'm going to, or you actually are turning the page, I'm going to go ahead and erase so we can get ready for example 7. All right, for number 7, we have the integral of pi dx. So what we're looking for here is what would we take the derivative of to get pi. We've seen something similar to this before. But what I'm going to do first is apply the constant multiple rule and pull the pi out. So we're going to get pi times the integral of 1 dx. And with that integral, we know that the integral of 1 dx is going to be x. So we get pi times x plus c. And that makes sense because if we take the derivative of pi x, we will just get pi. All right, number 8. We have the integral of 15 e to the x dx. Going to apply the constant multiple rule again. That's going to give us 15 times the integral of e to the x dx. Now the antiderivative of e to the x will be e to the x because the derivative of e to the x is e to the x. So we'll get 15 e to the x plus c. And there's that antiderivative. If we check, and we take the derivative of 15 e to the x plus c, we would get 15 e to the x plus 0. So that would be 15 e to the x. All right. And now we are ready for our next example, number 9. We have the integral of x to the negative 4 dx. So we're going to apply the power rule again, but the power rule we're going to be applying to this negative exponent. We've already done that a couple of times with x to the negative 2. We just had to do some adjustments first before we got to the negative exponent. We don't have those adjustments to do this time. So we're going to get x to the negative 4 plus 1 over negative 4 plus 1 plus c. So this will give us x to the negative 3 over negative 3 plus c. So I'm going to rewrite this as negative 1/3 x to the negative 3. That is one way we can rewrite it. We can also rewrite this as negative 1 over 3 times 1 over x cubed plus c. And that really looks terrible, so I'm going to rewrite that. This would be negative 1/3 times 1 over x cubed plus c. Or we can write that as negative 1 over 3x cubed plus c. So there we go. Now I do want to say at this point, as you're writing things down and thinking about what's going on here, I know from experience that at this point when we're talking about the power rule, we've talked about power rule for derivatives and for integrals. It is easy at this point, especially because we're talking about antiderivatives and derivatives, to get confused as to which thing we're doing, whether we're finding an antiderivative or a derivative. Well, whenever you see an integral sign, that means antiderivative. But also with the power rule, when we take a derivative, the power decreases. So D for decreasing. And when we're looking at an integral, the power increases. So it's just a little trick to help you remember what happens. All right, we're halfway through our examples. So on to number 10. We have the integral of 1 over x to the 5th dx. What we're going to do here is we're going to, again, rewrite the 1 over x to the 5th in the exponential format so that it is easier for us to approach with the power rule for antiderivatives. So we're going to have the integral of x to the negative 5 dx, and now we can apply the power rule. So we're going to get x to the negative 5 plus 1 over negative 5 plus 1 plus c. So that's going to give us x to the negative 4 over negative 4 plus c, which we can rewrite as, if we want, as negative 1/4 x to the negative 4 plus c, or we could write it as negative 1 over 4 x to the 4th plus c. And there we have it, number 10. All right, number 11. We have the integral of 3 over the square root of x dx. And the first thing I'm going to do here is to apply the constant multiple rule and pull the 3 out. So it's going to give us 3 times the integral of 1 over square root of x dx. Now this 1 over square root of x, we want to convert into an exponential form so that we can apply the power rule for antiderivatives. The square root is going to give us a 1/2 power because it's in the denominator. That's going to be a negative exponent. So we're going to get x to the negative 1/2 as the integrand. So we have 3 times the integral of x to the negative 1/2 dx. And now we're going to apply the power rule for antiderivatives. So we're going to have 3 from the constant multiple rule. And we'll get x to the negative 1/2 plus 1 over negative 1/2 plus 1 plus c. So that's 3 times x to the 1/2 over 1/2 plus c. And I'm going to simplify this. That 1/2 in the denominator flips up, and we'll have 3 times 2, which is 6x to the 1/2 plus c. Or we can go back to the square root notation and have 6 times the square root of x plus c. So there we go. All right, and now we're going to move on to number 12. All right, number 12, we have the integral of x squared times the quantity x minus 2 dx. All right, now for this, we do not have a product rule for integrals. We have a product rule for derivatives, and remember, it does not work just like derivative times derivative. We have something more complicated. The same thing applies here for antiderivatives as well. And really, you could think of the product rule for antiderivatives as being integration by parts, which you will learn in Calc 2. We're not going to talk about integration by parts this semester. So we need to do something to this integral to put it in a form that we can work with. What we're going to do first is we're going to multiply out. So this will be the integral of x cubed minus 2x squared dx. And now that we have distributed the x squared, we can break this up into two integrals. That is our sum and difference rule for integrals. So we'll get the integral of x cubed dx minus the integral of 2x squared dx. And that too, we can apply the constant multiple rule and pull that out of the integral as well. So we're going to get the integral of x cubed dx minus 2 times the integral of x squared dx. And now with that x cubed and x squared as those two integrands that we're looking at, we can use the power rule for antiderivatives directly on those terms. So we're going to get the integral of x to the fourth over 4, that's from our 3 plus 1 over 3 plus 1, minus 2 times x to the third over 3, so that's our 2 plus 1 over 2 plus 1, plus c. So I'm just going to rewrite the format here, you don't have to, but just so you see it in another form, we're going to have 1/4 x to the fourth minus 2/3 x to the third plus c. And there's our antiderivative for x squared times the quantity x minus 2. But remember that you do want to go ahead and distribute. Now at this point you might be starting to get to the point where you're thinking, okay, do I have to separate everything out? And the answer is no. As soon as you are comfortable and confident and feel good about exactly how those rules work, you don't have to do so much separation and individual writing down, but it's a really good idea until you are completely comfortable with how things work. All right, our next example, we are 2/3 of the way through, so we're getting there. We have the integral of x to the fifth plus 2x to the fourth minus x cubed over x cubed. So here when we look at this integral, it is clearly a quotient. We are looking for what in the world did we take the derivative of to get this quotient. And we know that when we take the derivative of a quotient, we have to use the quotient rule, and we do end up with a quotient there. We're kind of hoping we don't have to worry about that in this case because that makes things more complicated. But what we are going to do first, before we have to go down that pathway and try and think of something complicated, is we are going to see if we can simplify the integrand. And because we have this fraction here with only a single term in the denominator, we're going to break it up into individual parts and see what we can do to simplify. So this will be the integral of x to the fifth over x cubed. I need to rewrite that because I did not do a good job. So we can leave this all in one integrand, just break up the fractions. So we're going to have x to the fifth over x cubed plus 2x to the fourth over x cubed minus x cubed over x cubed dx. And now we're going to cancel the powers we can cancel. So we have x to the fifth over x cubed, and that's going to give us an x squared. And then we're going to have 2x to the fourth over x cubed, so that's going to give us a 2x. And then we have x cubed over x cubed, so those cancel and give us a 1. So now we have x squared plus 2x minus 1 dx instead. And I'm going to go ahead and skip the step of separating everything. We're just going to go one term at a time. So we're going to have the antiderivative of x squared using the power rule for antiderivatives. We're going to get x cubed over 3. And then we're going to have 2, using the constant multiple rule, times the antiderivative of x. So that's going to be x to the 1 plus 1 over 1 plus 1, minus the antiderivative of 1, which we know is x. We'll have plus c, and I'm going to clean this up a little bit. We can write this as 1/3 x cubed plus, we're going to get 2x squared over 2. So then the 2's will cancel, minus x plus c. So we end up with 1/3 x cubed plus x squared minus x plus c. All right. So there we have it on number 13. All right, number 14. We have the integral of negative 8e to the x plus 4 minus 5 over x plus 7 minus 5 secant squared of x plus 6 dx. Okay, so here we want to be thinking about what happens in various cases. Because what we've got here are things that look a lot like the antiderivative rules that we have. We've got something involving e to a power. We have a 5 over something. We have a secant squared of something. So we should be thinking kind of about the chain rule here, but we want to think about what would happen if we were to take the derivative of a term like this. So we have x plus 4, if in the exponent there, if we were to take the derivative of e to the x plus 4 using the chain rule, we would get e to the x plus 4, and then we would multiply by the derivative of x plus 4. Well, the derivative of x plus 4 is just going to be 1, so we're going to get e to the x plus 4. So right there, for our e to the x plus 4, it looked like our e to the x thing in our derivative rules, just with the adjustment of the x plus 4. And it turns out if we take the derivative of that, we still get e to the x plus 4, so that derivative and antiderivative rule still works the same if we have x plus something in the exponent instead of just x. Alright, so now let's think about this 5 over x plus 7. That looks kind of like our derivative rule where we have 1 over x, our antiderivative rule where we have 1 over x, and the antiderivative of 1 over x would give us natural log of x. Okay, so let's think about what would happen if we had x plus 7 in the natural log function. So we'd have natural log of x plus 7. Well, what do we get when we take the derivative of that? The derivative of a log function is 1 over the inside stuff times the derivative of the inside stuff. So we'd have 1 over x plus 7 times the derivative of x plus 7, which is 1. So that would give us 1 over x plus 7. So this 5 over x plus 7, well, the 5 is a constant multiple. So we can still apply this antiderivative rule, this 1 over x of natural log of, to be natural log of absolute value of x, if we have x plus 7 or x plus something instead of just x in the antiderivative, or in the integrand there. Okay. All right, so now we want to look, we should be suspecting the same thing is going to happen over here with the secant squared term. So I'm out of space, I'm going to erase here. We want to think about the secant squared. So with that secant squared, if we're looking on our antiderivative table, then we're going to see that the derivative, the integral of secant squared of x, the antiderivative, is going to be tangent of x, which does not surprise us because the derivative of tangent is secant squared. So let's think about what would happen if we had x plus 6 in there instead of x. So if we have tangent of x plus 6, and we take the derivative of it, That's going to give us secant squared of x plus 6. And then we would multiply by the derivative of x plus 6. But the derivative of x plus 6 will just be 1. So this would just give us secant squared of x plus 6. So again, adding something to the x does not change the sort of thing that happens with the antiderivative. Instead of integral of secant squared of x dx equal tangent x plus c, we would have integral of secant squared of, say, x plus 6 dx is equal to tangent of x plus 6 plus c. So now we're going to apply those three things we've just looked at to find our actual antiderivative. I'm just going to jump down to the bottom here and write that in. So the negative 8 we're going to pull out. That's a constant multiple, so we'll just have the negative 8. And then we talked about antiderivative of e to the x plus 4 is just going to be e to the x plus 4. For the negative 5 over x plus 7, the negative just kind of comes along with it. The 5 is a constant multiple, so we get negative 5. And then we're going to have the natural log of absolute value of x plus 7. That's our antiderivative rule with the absolute value in there. And then with the secant squared, we have negative 5 out in front. So we're going to subtract 5, that's our constant multiple. The secant squared antiderivative is going to be tangent. And we're going to have tangent of x plus 6 plus c. And so there's number 14. All right. We are nearly done. Only a few more to go. All right, we are ready for number 15. Number 15, we have the integral of 6 sine of x plus 5 dx. So we get a little bit of a break after that last one, which was a little more complicated. We've got a constant multiple of 6. And then we have integral of sine of x plus 5 dx. So I did the constant multiple rule that time. And then with that x plus 5, we still have the same thing applying as we were just looking at in number 14, where if we have x plus a number, then the antiderivative rules we can still apply with x plus a number, replacing the x in there. So we need to know what's our antiderivative of sine. In other words, what do we take the derivative of in order to get sine? And that is going to be negative cosine. So we get 6 times negative cosine of x plus 5 plus c. And then that negative, I'm going to pull out in front so that we don't make any mistakes and look at this and think it's subtraction. We are actually multiplying there, so that's negative 6 times cosine of x plus 5 plus c. And again, I am writing some extra algebra steps as we go along. If you are confident and feel good about your algebra, you don't have to write as many steps. All right, 16. We have the integral of 7 cosine of x plus 5 plus 1 over x plus 8 dx. All right, the x plus a number, again, we treat the antiderivative rules the same way. We just replace the x with the x plus the number. So here we're going to have a constant multiple of 7. I'm going to write that down. We need the antiderivative for cosine, and that's going to be sine. So we're going to have sine of x plus 5, because of the x plus 5 inside of the cosine. And then the 1 over, that is going to be a natural log. So we're going to have plus the natural log of absolute value of x plus 8 plus c. All right. 2 more to go. 17 and 18. I hope that these are starting to seem a little more comfortable getting the idea of what to do with them. But I will also say that the only thing you can do to get really good at these is just do a whole bunch. So just keep practicing. You can do it. 17. We have the integral of 5 sine of x minus 6 plus 8 cosine of x plus 9 dx. So we're going to be applying the same principle we've been applying. We have x plus a number, I know it looks like subtraction, but we're just adding the negative. And then we have x plus 9. So we're just going to apply the constant multiple rules with the 5 and the 8. And then that same principle to find our antiderivatives. The antiderivative for sine will be negative cosine. So I'm going to have negative 5 cosine of x minus 6. Antiderivative of cosine is sine, so we're going to have plus 8 sine of x plus 9 plus c. All right, that's 17, and that brings us to number 18. And this is the integral of, I'm not starting out to write that in the right spot. Integral of 7x squared minus 3x to the 5th plus 4x over the square root of x dx. So the first thing we're going to do is, just like in number 13, I'm going to separate this into individual terms because we have only one term in the denominator. I'm going to separate this so that we can simplify the exponents and apply the power rule to each term. So we're going to have the integral of 7x squared over square root of x minus 3x to the 5th over the square root of x plus 4x over the square root of x dx. All right. Now, the square root of x, we really want to be thinking of that as in its exponential form so that we can simplify the powers. So we're going to remember here that square root of x is equal to x to the 1/2. So now I'm going to go on to the next line here. We're going to have the integral of 7. So if we have x to the 1/2 over x to the 1/2, we're going to subtract the exponents. So 2 minus 1/2 will give us 3/2. So we get x to the 3/2 power. So that's a term that we can work with fairly easily with the power rule. Minus 3, and then we have x to the 5th over x to the 1/2. So we're going to subtract the exponents. 5 minus 1/2 is going to give us 4.5, which is 9/2. So we have minus 3x to the 9/2. And then we have 4x over square root of x, in other words, 4x over x to the 1/2. So that's x to the first power. We're going to subtract the exponent. 1 minus 1/2 gives us 1/2. So we get 4x to the 1/2 dx. And now we are ready to find the antiderivatives of each individual term using the constant multiple rule, and then the power rule for exponents. So this will give us 7x to the 5/2 over 5/2 minus 3x to the 11/2 over 11/2. Either way. Plus 4x to the 3/2 over 3/2 plus c. And now I'm going to go back up at the top and rewrite that. And all of those fractions in the denominator, we can invert and multiply. So 7 over 5/2 will become 14 over 5, x to the 5/2. 3 over 11/2 will give us 6/11, x to the 11/2. And then 4 over 3/2 will give us 8/3, x to the 3/2 plus c. And that's it, the end of our examples.